This video goes over characteristics of the normal distribution, which is our fifth distribution that we've talked about, and has some pretty important applications when it comes to analysis and manufacturing in the real world. The example here is about a potato chip company, and it has a packing machine that fills 200-gram bags. The quality control department selected 70, and their masses are down below. We also have a histogram showing the masses of these chip bags. So some observations that we can make here is that the graph peaks in the middle. It is unimodal, or has one mode. It's pretty symmetrical. Not perfect, but pretty good. And then we have a bell-shaped curve. What that means is I can sort of draw a curve that goes above the data and then down on the other side. And so we say that this data is normally distributed, and then we're going to investigate that a little bit further. So the first thing that we're going to do is calculate some other one variable statistics. So what I've done is I've typed all the weights into Excel here or Google Sheets, and we're going to calculate some using our tool. So the mean chip bag. So let's type in here. We want average, and we're going to go from A2 to A71. Oh, there we go. And if I press enter, I can see my mean there. I'm going to go through and calculate the other ones before I go on. So now I've got the standard deviation. So S, T, D, E, V. And I'm going to use the same range. So A2 to A71, which is my range there. Just doesn't quite show up on the screen. And then I'm also going to find my median. So equals, I'm going to start typing out median. It shows up right there. I'm going to enter the range that I want to calculate, A2 to A71, same as before. A2, A71. There we go. So now I've got some data that I can put in here. I know that my mean chip bag is approximately 209.9 grams. My standard deviation is about 3.82 grams. My median weight is 209.9, same as my mean. And then my modal interval I can get from my table. I know it's this one right here. And if I follow that all the way down, that goes from, let's see, 10.5 to about 11.5. So 210.5 to 211.5. So that one's just read from the graph. So these three were sheets and then read from graph. So now we're going to continue investigating the spread of the data from this particular sample. So X minus 1 standard deviation. So what percent of the data is that? So let's go here. So I've got X is going to be between my mean plus my standard deviation, or I've got X minus my standard deviation here. So that means that on the left-hand side, my range is going to be 209.9 minus 3.82, which is going to give me 206.08. And let's see, I'm just going to rewrite that so it's more mathematically accurate. So on this side, I've got 209.9, take away 3.82, and that's going to be less than or equal to X. Now on the other side, I've got 209.9 plus 3.82. So I've got 213.72. And then what I'm going to go and do is go ahead and highlight the data that is between those values. So 206.08 and 213. So let's make that a little bit darker, I think, so we can see it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, let's see, 45, 46, 47, 48, last column here, 49, 50, 51, 52, 53, 54, and 55. Holy smokes. Okay, so we've got 55 out of 70 pieces of data, which is going to translate to about 78%. We're going to continue the pattern down here for x plus 2 sigma and x plus 2.5 sigma. We've highlighted the majorities, so it should go a little bit faster here. We don't need that anymore. So let's go x plus 2 sigma. So now I'm going to have x less than or equal to 209.9 plus 2 times 3.82, which is going to give me 217.54. And then on the left-hand side, I'm going to take away 2 sigma. So 209.9, take away 2 times 3.82, gives me a lower value of 202.26. Okay, so let's go back up. I'm going to highlight in a different color this time. So all the way down to 202, all the way up to 217. So I've already highlighted 55 pieces of data. So let's see. So 56, going down to 202, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, and let's see, 67, and that's it there. So now I've got 67 out of 70 pieces of data. I'll write that in my marker here, 67 out of 70. which gives us 96% of the data. So now if we go, let's see, we only have one more piece there. We don't need to do this one here. So here, if we expand by another sigma, we're going to get 100% of the data, or 70 over 70 pieces. So that is for our particular sample. Now this has been done over lots of normal distributions. So in general, X bar plus or minus sigma accounts for about 68% of the data. X bar plus or minus 2 sigma accounts for about 95% of the data. And then X bar plus 2.5 sigma accounts for about 99% of the data, or most of it. So we're going to use the properties above to make conclusions about any normally distributed set. So we'll go through a couple of examples here. The first one is the heights of 1,000 university females are normally distributed with a mean of 165 centimeters and a standard deviation of 15 centimeters. Find the number of women with heights between 150 centimeters and 180 centimeters. So this is one standard deviation on either side of the mean. So that means that it's about 68% of the data. Visually, we would represent it like this, about one standard deviation. And so to find it, we would do 68% of 1,000 is going to equal about 680 women. The next one asks us to find heights less than 180 centimeters. So what I have here is that 1 sigma above, so this is my 180 centimeters, which is 1 sigma above, and 1 sigma below in total is going to be 68. So I can say for sure that this part here is half of 68, which is going to be 34%. Now, I can add it to this whole rest of the other side of my graph, that this is going to be 50% of the data. So what I can see here is that the total area under the graph accounts for the number of women that have heights less than 180 centimeters. So 84% of 1,000, which is approximately 840 women. So let's do one more. We've done a between, we've done a less than, now we're going to do a greater than. So if we sketch our normal distribution, we're looking for heights greater than 202.5 centimeters. So this is 2.5 standard deviations to the right. Okay. So if we've got 2.5, so 1, 2, and then 0.5 here, we only have, so between here, if I go between, this is minus 2.5 and this is plus 2.5, this whole part accounts for 99% of the data. That means that this plus this has to equal 1%. They are symmetric, so each piece there accounts for 0.5%. So that means that the number of women that have heights greater than 202.5 are only 0.5% of the sample of 1,000, which is only 5 women. Example 2 is going to ask us to go the other way. So find the percentage of data that lies within 1 to 2 standard deviations to the right of the mean in a normal distribution. So let's do a sketch to represent it here. So I've got my normal distribution. Here I've got 1 standard deviation, and here I've got 2 standard deviations. And what I'm looking for is the area between those 2 boundaries. So what I can do is I'm going to do my area for 2 standard deviations, take away my area for 1 standard deviation. And what that's going to leave me with is the difference between the two. But it's going to leave me with a difference between 2 on both sides, and we'll show that in a minute. So if I do 95% minus 68%, that is going to leave me with 27% of the data left over. But we're only looking on the right-hand side, and this method gives me the total on both sides. So this is really what I found here. Those two areas added together. So that means that I need to do 27% divided by 2, which is going to give me 13.5% of the data lies within 1 to 2 standard deviations to the right of the mean in a normal distribution. That is all about a normal distribution, standard deviation, and the percent of data collected within standard deviations. Very important application in the real world in terms of manufacturing and scientific analysis.